All right. Hello, class. Welcome back to the part B of this lecture. So in this relatively short sub-part, I'm going to be talking about two sort of tangentially related topics, not explicitly connected to each other, so they're sort of random to some extent. So the first one is, so they exploit properties that we talked about in part A, but they're a little bit off topic, so I give them a little mini lecture here. So the first is the controllability Grammian. So, sorry, not the controllability Grammian, the controllability ellipsoid, which is derived from the controllability Grammian. So if you have the controllability Grammian, you get the controllability ellipsoid. And so we talked about the derivation of the controllability Grammian in the previous lecture. So here's the infinite time controllability Grammian, and for a finite time, we just replace that little infinity with a TF there. All right, so we'll ignore that for a moment. So we talked about in the previous lecture the fact that, or the previous part of the lecture, that we talked about the fact that if this system is reachable, right? So if there's a solution to the Lyapunov equation for reachability, then we can get to any particular state. And in fact, we found an explicit open loop controller which would drive our system from x of 0 to our desired state x of d. And in fact, we got the explicit solution there. That was u of t equals, well, that's on the next slide. B e to the a transpose tf minus t. And I think there's a transpose there. Wt inverse xd. All right, so make sure that's right. Yep. Okay. So we got an explicit input which would drive our system to this desired state. So now we look at a little bit about what we can do with that information, a little bit more how we can leverage this Lyapunov solution, this Lyapunov function embedded in the controllability Grammian, to sort of graphically understand which directions or which states are more controllable, so we can be quantitative about our controllability here. So that information is actually contained in the controllability ellipsoid. So it's an ellipsoid, right? And it's a quadratic inequality, less than or equal to 1. And this tells us what set of states are reachable, well, in time t, or ultimately reachable if we extend it to infinity, using an input of magnitude 1. And we haven't defined this norm here, but it's just a square integral of the size of the input. So with an input of energy 1, what set of states can we reach in either finite time or infinite time? Right? And that's the controllability ellipsoid. So it looks like this, right? And I'm taking this little picture here from Sanjay's lecture course. So we've got a couple things happening here. So first of all, we've got directions. So these are the directions, and those correspond to the eigen vectors, or the singular vectors, because in this case W is a symmetric matrix, and so they're the same thing. So there's the let's call them the eigen vectors to make life easier. And then so that's the direction, and then the length of that direction, the distance we go to get to the controllability ellipsoid, is the square root of the of that corresponding eigenvalue. So we can call this v1, for example, or v1. I guess that's v2. So what does this tell us, right? Well, it tells us a couple of things. So it says that basically longer if this length is longer, then that direction is more controllable. Well, why does it tell us that? It means it means we can get farther in that direction with an input of unit 1, right, of energy 1. So if we wanted to go this far, when we only have 1 unit of energy, we can get farther than if we wanted to go this direction and we only have 1 unit energy. So for the extreme example, of course, is the case where the eigenvalue is 0, or the singular value is 0. And in that case, it would be completely flat. We couldn't get there at all, right? We can't go in that direction at all. We can only go this direction. And of course, we can generalize this to n dimensions. It's not just two-dimensional problems that we consider here. Okay. So there's the proof of that is rather it's not terribly complicated. It's on this like little set of note slides here, where we just take that input, right, that we got from the previous slide, this open loop input, and we just measure how big it is, right? We just take its norm, we square it and take its integral. And then if we actually plug that in here for u, right, well, that pops over here. And then we can pull the integral inside right there and partition that off. Sorry, partition it off there. Right. So that we get this integral inside that square, and of course this is just the controllability Grammian itself, and so we get this expression here. The w's cancel here, and so we get this is the size of the input that drives us to state x of d. Right. So that tells us if we're inside this ellipsoid, right, we can reach any of these states, wherever they happen to be, anything inside that ellipsoid with a unit energy. And of course, you can expand the ellipsoid if you have more than 1 unit energy. You just double the size of it, and so forth. All right. So that's a nice result, and of course you get the Grammian by the solution here to this Lyapunov equation, which is technically not a Lyapunov inequality, it's just an equation, but we can extend it actually to less than or equal to 0. But if we solve this equation, that's the solution we want to use for our Grammian. So there's a couple different ways of viewing, deriving the information that I stated, right? So for example, if we go down here to this last comment here, so in this case the eigenvectors and eigenvalues are the same, so we just do an SVD of the Grammian. The inverse of the Grammian is remember these are unitary matrices here. So the inverse of u is just u transpose, and so we get the decomposition of the inverse. And hence, if we have if xd is an eigenvector, or a singular vector, if you like, a unit singular vector, and I should emphasize that. So of norm 1, then right, then u with u transpose that doesn't change size. And we just multiply it by that inverse singular value here, right? And so we get that the energy required to get to that singular vector is just what we have here, which was what we saw in the Grammian. So that's just a short derivation of the controllability Grammian. So we'll come back to ellipsoids again when we do observability briefly in the next lecture. For the observability ellipsoid, of course, which doesn't have an inverse in there, so it's a slightly different interpretation. But there's not that much to it. It's a relatively simple concept, and it allows us to quantify how controllable some directions are with respect to others. So it's a nice concept. The second item that we want to discuss today is, or in this subpart, is stabilizability, and this is a little bit, again, off topic. So stabilizability is a little bit weaker than controllability. So basically, it says that a pair, right, a system, is stabilizable if for any condition there exists an input which will get you to 0. So of course, if the system is stable, right, all trajectories converge to 0 anyway, so you're done. So it's this is weaker than stable, right? So stabilizable. So it basically says that anything which is not already stable, there's an input which you can stabilize that. So in this case, you only need to stabilize the states which are not naturally stable. Right. So again, right, weaker than controllability because, right, we don't have to actually, we don't have the ability to, for those states which, right, naturally decay, we don't have the ability necessarily to push them in various directions. They naturally tend to 0, and so we abrogated that ability. We only need to approach 0. We don't need to go anywhere else. So there's an LMI for this. It's, again, slightly different than the LMI we had on the previous slide. And I want to emphasize that difference in that on the previous slide, right, we had BB transpose as well. But in this case, we had a plus here. And in this case, we have a minus, right? So it's very similar, but it's not quite the same. And the difference is important because when you move if you move this gamma BB transpose to the other side, right, you get less than gamma BB transpose, right? And so that means that the AX plus XA does not necessarily have to be negative definite. So it can be positive for certain subspaces, so basically spaces which are ignored by the input. So those are not ignored by the input. So those spaces are naturally stable anyway. Furthermore, you can go say something a little bit more, right? You can say if you have a solution to this this inequality, that gives you a stabilizing controller. So much in the same way as similar form of the controller that we had before, a stabilizing controller in this case is given here. Just take that inverse of the Grammian, apply it to the state, and you put a B in front of it. And there's a negative sign here. Don't forget the negative sign. These signs switch back and forth, right? Common mistake is people mess up the negative signs. So this is interesting in a couple ways. First of all, of course, it's a feedback controller, right, as opposed to an open loop input, right? Before we had an input that looked like, right, this. There's a B transpose here and a W inverse with this other stuff here. So that was getting us to a particular state, right? Here, so that was open loop. Here, we're responding to where we are at the current state. So even if, right, your knowledge of the system is faulty, or you don't know exactly where you are, right, you can still use this feedback controller, and presumably it's a little bit more robust than that open loop controller here. So feedback controller. So the proof of this is actually is quite interesting. It's similar to the proof we had before for the controllability Grammian, but actually the solution to this Lyapunov inequality, right, the solution X here, it turns out to be what we call the reverse time, or I call the reverse time controllability Grammian. So basically, instead of having the positive AT, so reflecting a solution, right, how the input affects the solution, it's actually goes backwards in time, so we put a negative sign in front of the A here, and actually that carries over to the S. So it's moving sort of backwards in time. It's the opposite effect, which makes sense, right? Instead of going from 0 to a point in the state space, we're going from a point in the state space to 0. So it's sort of the opposite, the reverse of the original controllability Grammian. So the solution to this, right, does not have, of course, you can't use that to get the this controllability Grammian. It's a different solution entirely. All right. So again, right, very brief digression onto two interesting but a little bit tangential subjects, and I'll close this quick introduction to those two subjects, and then start up part C with eigenvalue assignment problems.